Right. I would like to introduce our next speaker, Dr. David Barbee. He is the Director of Technology and Innovation in Radiation at NYU. And again, he has been an early adopter of our product. He has done a lot of the initial testing. We have utilized his expertise, and we are thrilled to have him here on our show floor to share with you what he has found in testing this new product for us. So thank you, and I turn it over to you.
All right. Thank you, Dana, and thank you, Raj, for the great intro to the product. So first, some disclosures. NYU Langone Health is a SNC's Mirion Center of Excellence, and I did receive travel support to present here today. So as Raj pointed out, right now the status of daily QA is we have a lot of different QA devices that are all siloed and not really talking to each other. So we test each of these components individually. And so you can see I've got IGRT, your beam, your Winston-Lutz maybe. And notice I don't even have SGRT on here because it's really just a checkerboard phantom for us, so it's not really integrated at all. So the folks at SNC recognized that there were major gaps in daily QA with all the technological advancements, so they came out with this daily QA 4, which is the next generation of daily QA platform. So the goal here is to combine IGRT, SGRT, dosimetry, and isocenter analysis into a single reproducible setup. So Raj has given you a background, so let me just jump right into it and talk to you about the SunCheck workflow. So first, Daily QA4 integrates with the SunCheck environment. So you can have either an enterprise solution for all your machines, or you can have a local one just to run your single Daily QA4. For those of you that are familiar with the SunCheck platform, it works off of template tasks, and you can see that there are two new ones specific to the Daily QA4, and those are active measurement and imaging measurement. So in the active measurement, you see we have the typical dosimetry for photons and electrons, and then that new active measurement Winston-Lutz, which is using the diodes placed around the device in order to calculate your isocenter. For the imaging measurements, we've got our typical positioning, repositioning, where you test your image guidance, now using the Phantom for all of that, as well as the imaging Winston-Lutz, which is using those fiducials for the KV and MV panels. And I want to show in the workflow down here on the bottom, and I've got little door symbols signifying when you go in the vault. So when you go in the vault, you set it up, and then you walk out, and you perform all of your IGRT, SGRT. So if you have electrons, you skip the next going in to put the cone in, but in this case we have cones. So I'd go and put the cone in, take it out, and then we leave it all in the same position for all the rest of the tests. And so doing this, we were able to test our Vision RT, our IGRT, 4 photons and 5 electrons in 11 minutes, which is about 5 minutes faster than when we're swapping all the different phantoms. Without the electrons, it goes much, much faster. After you're done with that, you have a choice where if you want to do a Winston-Lutz test, you can use either the active measurement, or if you want more in-depth information, you can do the imaging Winston-Lutz. And the active measurement, because of those automations that Raj mentioned, you can do those in about 5 minutes with really one button click. For the imaging Winston-Lutz, it's a little bit longer because it can't be automated, you'll see in a second. And so that one is 12 minutes, or if you have developer mode, I've written a script now that completely automates the delivery, and you're able to do it in only 7.5 minutes. So those Winston-Lutz measurements with this device, they cut our time basically in half for each of them. We really save about 15 minutes in compared to the multi-met Winston-Lutz cube. And it's very important to note that when you're doing this workflow, it's with the 6DOF base plate, and you're doing all of these Winston-Lutz tests with applied pitch and roll, which we don't typically do. So now let's get into the IGRT position reposition. So this is very familiar to those SunCheck users that do this already. It's got the familiar KV, MV, and your CBCT, all those types of registrations. But it's also got fields that you can enter yourself for things like SGRT, SSD, and your residuals on SGRT for after you've done your shifts. You can also measure either displacement or isocenter position for iso shifts, or absolute couch position, or zero-based residuals. On the top right there, you can see an example of the Phantom CBCT with that 6DOF base plate, which has 1.5 degree rotations in yaw, pitch, and roll. And the 6DOF base is optional, but as I said, including it during this step allows those translations and rotations to propagate through all the rest of your QA. And this is an example of one of the polar plots, the rose plots that they give you at the end, where it shows each of the different imaging systems and the walkout isocenter for each of them. So one of the first things I did was looking at the SGRT, because we don't really have a Phantom that's capable of doing things like this. And so I tested out the boundaries of how far it could image within the SGRT bounding box. And I found that it could go lat and long by 4.5 centimeters and about a 20 centimeter range for vert. And a lot of that is because there's a symmetric pattern in the recesses on the surface of it, so that once you move 4.5 off, then it starts to pick up the next recesses as that one. But we don't typically use shifts that much. We're really looking for 1 to 2 centimeters, so it's not really a concern. Also, when you rotate 45 degrees, due to symmetry, it starts to pick that up as 0, but it picks up perfectly once you hit 90 degrees because the SGRT system is able to recognize that. And here you can see that I'm moving it around and working with the actual machine. And this, when I was doing this, I realized it was really the first time that we have linked our IGRT system with our actual couch movements with our SGRT system. The SGRT is we haven't really tested pitch and roll and yaw with everything all in one phantom. So the next thing I want to go over is array normalization, because with every SNC device, it's always a question of how many array normalizations am I doing? And how do you have to do it? So this is completely new as well. Instead of the shift-based, where you have to do multiple exposures to figure out what the array's normalization is going to be, this is now using a prior measurement-based calibration procedure. So the idea is you take a water tank scan that defines your beam, or an IC profile, or even any manual CSV, and then you use that for a basis for your array calibration. The requirement then is that the daily QA4 must match the geometry that you took that profile in. So here's an example of an SSD calibration where I'm taking the IC profiler, measuring that, and just putting that file into the software and then irradiating, and that gives me the array normalization in just one single step. You can also do it isocentrically with buildup on top or without buildup on top, or you can use a water tank scan from any vendor with an ion chamber. And so I did this with multiple different setups, and an example here is the factory 6X that they give you, along with an SAD without any buildup on it that we use for steering, and then a 9010 SAD measurement. And you see that there's nearly perfect overlap, so it's very, very consistent. So then I looked at all of the energies to see how it varied. On the left, you'll see that those are raw array normalization profiles taken from that steering, because you can't really measure electrons with that much buildup, so I went with no buildup. You can see there's pretty decent overlap and not a lot of variability. And then over on the right column is all of those array normalizations normalized by just the 6X. And you can see that they're for the most part, within 2% for the photons. Electrons are nearly all within 2%, just some edge issues there due to the electron cone. But this gives me confidence that you can use just a 6X array normalization, because after this you're going to be setting baseline, and then it's just going to be shifts based on that baseline. So it's going to be an even smaller difference than this. Next, I wanted to test out the detectors, because there are a lot more detectors in here than the daily QA3. And so I looked at task group 3112, which is for the acceptance and commissioning of both ion chamber and diode arrays. And I looked at the dose linearity, dose rate response, reproducibility, leakage, and rotation of the array normalization, and then also dose calibration. And you can see that for the most part, everything worked out very, very well. The only one kind of gotcha was on the dose rate response. And sorry, just to clarify this, the ion chambers, the 4 ion chambers that are centrally located, are the dots all the way on the left. Everything else after that is either the it goes the x-axis, the y-axis, and then the diagonals. So in the dose rate response, you can see that the ion chambers perform perfectly well, which is really what you're concerned with when you're testing dose rate response. But the diodes showed some dose rate response, where the dropping the 6 MV down from 600 to 100 dropped the response by 2%, and dropping it down to 20 MU per minute fell off the chart here. But that's not really an issue, as I said, because we're really using the ion chambers for those types of tests. Important to note, though, that some of these tests require irradiation of the entire surface, which can't be done in the standard QA test due to those field size detections, where it will detect that you're irradiating more than you should be, and it will actually stop. Similarly, leakage can't be performed because of that trigger, where it thinks that the measurement's done and it tries to move on to the next one. So I had to work with Raj to use some developer software to actually take these measurements. Now let's look at dosimetry. A lot more detectors, so there's new metrics that are available. Things like a penumbra, beam shape, constancy for the FFFs, beam center, DPSI, and dose per pulse. The energy calculations now use those wedges, and you're now able to measure over a wide range of 2 to 20 centimeters for those square fields. There's also a new dose output correction factor that you can use when moving the device across machines in case one fails and you need to move things around in one morning. And there are also those new features for automation with Auto Advance, the trigger, and the field size detections previously mentioned. And that automation and trigger allow for one-click execution of all the beams and energies. One thing that you might not notice is for the setup here, they've now indicated the field size using the MLC because it's a little bit more robust and accurate, but I've always done JAWS, so the first thing I wanted to do is test out whether you had to use MLC or JAWS and what those differences were. So I tested out all of the parameters across 6 machines and all 5 of our photon energies in 30 sessions using both the JAW and the MLC. And on the left here, you can see those are the output factors, and they're very, very consistent once you get down to, about 7 centimeters, you start to see a little bit of differences with a little bit tighter on the MLC than the JAW, a little bit less variation. Otherwise, everything is very, very consistent across both of them, with the exception of the very small fields when you start to see the symmetries deviate at 2 centimeters, and also in the penumbra, where the JAW settings were. The JAW penumbra was larger than the MLC, which makes sense because the JAW is much higher on the machine. Geometric penumbra is going to lead to wider penumbras. So all these looked great, and we decided to go forward with the MLC testing for future. So now let's get into the active measurement Winston LUTs. As Raj pointed out, this is using all the detectors in the array, and you have a choice of irradiating using either 8 gantry angles or 4 gantry angles, or just the cardinal angles, along with collimator rotations and couch rotations. That requires that you use a smaller field size for that gantry to make sure that you don't over-irradiate the side panel detectors, so I used a 2x2 field for all of these. On the right there is an example of the delivery field that I put together for machine QA. And the TrueBeam users would probably recognize that that green line there means automation, where it automatically advances to the next irradiation without any prompting. So when you combine these things, you're able to actually just hit start, the play button there and the little animation in the bottom, on the SunCheck software running the Daily QA4, and then you start your delivery and they just move all the way down until you have to do your couch kicks for the Couch 90, which you can't automate. So doing this it truly turns it into really a one-click solution. So that looks great and it's very fast and efficient, but does it work? So in order to test this out, I looked at the sensitivity for positioning errors. So in this case, I went out to, I introduced shifts to the Phantom in 0.5 millimeter intervals out to 1.5 millimeter on 2 different Linux and 20 measurements, moving each one of the axes independently. Doing this, I saw that there was excellent congruence between the measured deviation and the driven distance, and I also used the undriven distance, the one that should be stable, as a noise floor calculation. So I took all of those together, put them together, and saw that there was a noise floor of about 0.07 millimeters, which means that you can also that it basically has a minimum detectable shift of 0.14 millimeters with a 95% confidence interval. So it is able to measure these very, very well. However, there is one gotcha that I discovered very late in the game, and that's gantry and roll angle sensitivity. Because we're no longer taking these Winston LUTs measurements at the isocenter and we're moved out laterally with that side panel detector, it now introduces, it now has a sensitivity to gantry angle that you wouldn't normally have with a BB. And so I've got an equation here for simple trigonometry for what that deviation is going to be, and it turns out that if your gantry angle is greater than 0.2 or about 0.2, it creates a 0.5 millimeter vertical offset. And so the other point is that another point to make is that this is also going to be sensitive to phantom roll. So if your couch roll isn't perfect, then that can also add to this, or they could cancel out. But on the bottom left, there is an example of a good delivery, what we typically see, and then on the right is a gantry error delivery with a 1 degree gantry error induced. But the good news is that I didn't see this anywhere in all my testing. This is an example of 18 measurements across 6 of our Linux, so basically our entire fleet using both the JAW and the MLC, and I never saw anything, I didn't routinely see anything that was at 0.5. There's a slight bias in the largest spread in the Y direction, and that's most likely due to the limited resolution in that direction. Our planned CT is 1.5 millimeters. Our CBCT, the minimum we could get is 2 millimeters, and so there's a little bit of play in there, and that might have introduced a systematic error in our image registration that then led to this kind of bias in our Y direction. But the good news is that you can set a baseline and remove biases like that. So if you do have a roll in your CT scanner that is going to introduce that Y offset that I showed, that can be removed through a baseline. Next, I looked at the active measurement Winston-Lutz results compared to all our other Winston-Lutz measurements. So on the left is our SunCheck Winston-Lutz for all of our machines over a 1-year period, and then MPC geometry, MPC enhanced couch, and then that daily QA4 active measurement Winston-Lutz. So the values are very comparable, and this is earlier in the testing, and this includes all those jaw measurements, which are a little bit larger than the MLC. So they're definitely comparable. Next, I want to go over the imaging Winston-Lutz. So very similarly to active measurements, it's going to have 8 gantry angle, or 4 or 8 gantry angle irradiations, and then your imager, and then your collimator and couch rotations as well. So this is a look at the delivery plan that is required to generate these and the subsequent images that you have on the right. So it's 20 different irradiation steps with 8 kV for the gantry, and then 12 for the MV imagers. And on all of the MV images, there's a 2x2 field that's covering those 8 tungsten fiducials in the phantom. And unfortunately, delivery can't be automated for this, because when you do integrated imaging or any sort of imaging, you can't just step to the next one. But that being said, taking all these measurements, I didn't want to do this manually, so I created a developer mode script for TrueBeam that allows automated acquisition of all of these. So this is a look at what the results look like. For each KV and MV, you get per gantry angle errors, pitch, roll, the image panel offsets, phantom positioning, and on the MV you get the MLC center and the width, and then the field fiducial offsets in X and Y. But right now it's only for gantry at 0 and 180 degrees, not at each gantry angle. And the QA tasks for these are summarized by the max value, which is basically the worst value over all the different gantry angles, because it's a ton of information to try to distill into an actionable pass or fail. And on the top right, you see those are the KV images and the analysis, and then on the bottom right are the MV analyses. So now the question is, does this work? So I did a similar test where I moved it in 0.5 degree increments independently in each axis, again, and it accurately picked up the shifts with no problem, and it had an even lower noise floor than the active measurement with 0.05 millimeters and a minimum detectable shift of 0.1 millimeters using the same methods that I did before. And lastly, one thing that I wanted to look at was what was the image, the panel sensitivity. So I again introduced random gantry errors of 0.5 and 2 degrees here, which are shown in the orange, to look at how it deviated from the baseline, which is in the blue. And you can see that there are some slight differences. The orange breaks away at around the 90 and 270 degree angles for things like the image offset in the Y direction and the SID. But even more interestingly was I disabled ISOCAL in our TrueBeam, and I ran through these tests as well. ISOCAL is the thing that recorrects all the panels. And I saw that it actually matched up really well. So that we saw the MV panel shifts in the offset X direction were about on par with what we saw in the MV. And then the KVs, which were a little bit larger in the lateral direction, those were about on average a millimeter, and those were accurately reflected. So this is the first time I've really ever tested this and seen this. I don't know of any other Phantom that can really get down to the panel level like this and match up with ISOCAL. So in conclusion, the Daily QA4 integrates IGRT, SGRT, beam dosimetry, and Winston-Lutz into a single device, enabling comprehensive daily QA in a single setup and session. The active measurement Winston-Lutz reliably detected submillimeter shifts and is concordant with MPC and our traditional BB-based Winston-Lutz measurements across all of our machines. However, you need to be careful of the couch roll and gantry angle error, because those could affect your vert. And it wasn't X and Y, it was only the vert position that was influenced by any of those gantry errors. Imaging Winston-Lutz provides QA of the phantom positioning, KV imaging panel positioning, gantry pitch angle, MLC field width and centering, and fiducial target accuracy, but only at gantry 0 and 180. And the one thing on my wish list that it's missing is an analysis similar to the multi-met Winston-Lutz, where you have the field to target coincidence for all the different angles. There's a ton of information coming out of the multi-met Winston-Lutz that I'd like to see here, because this has even more detectors or even more spheres for calculating this. And the other one is that it's not currently doing that phantom offset or that phantom positioning offset with respect to couch, which I think it really needs to do. And lastly, significant workflow efficiency gains. We saw that just doing a regular IGRT, beam constancy, and we weren't even really doing SGRT besides the checkerboard. We were able to do all of that and reduce our regular QA time by 5 minutes over the current process. And then adding Winston-Lutz just requires another 5 more minutes. That is very simple because it's all in one setup, and your therapist is now able to do it as part of their morning QA with just 2 clicks. So I'd like to acknowledge the NYU team and Sun Nuclear Miriam for all their help in me testing this device. Thank you.